Good evening, everyone. Today is the 11th session of our lecture series on structural design of lightweight hybrid multi-story construction. And I would like to invite Vice President Engineer Mrs. Kamala Gunawardena to do the welcome. Over to you, madam.
Yeah, thank you, Engineer Banduka. Good evening, everyone. Good evening, Professor.
Good evening.
It's my pleasure to welcome you to this lecture again, especially for today's lecture. That's the, I think, 11th lecture, lightweight hybrid multi-story construction 1, right? So I think let me welcome our esteemed Professor Tishanjay Singha, Professor. Senior Professor, Department of Civil Engineering, University of Moratuwa. Your continuous dedicated lecture series and appreciate a lot. With that, actually, you will be taking our participants to a new era. I think it would be some sort of a great experience to the members, participants. Actually, you will be talking according to your abstract. Newly developed construction technology where the evolution can be dated back to mid-1940s. So definitely it will be a very interesting one. And with that excitement, I think we'll start the thing and I welcome our participants to the lecture. And I think with this, expecting more contributions and to go ahead with the same lecture series, I invite Professor Jayasinghe, Professor Tishan Jayasinghe to take over the platform.
Yeah.
Thank you,
Okay.
Professor.
Thank you very much. Thank you very much, Engineer Kamala.
Thank you.
Thank you. Good evening, everybody. Now we started by looking at the basic materials that we use, and also we looked at how the Eurocode can be used for design of beams. And the moment we know how to design a beam, designing a slab is not a major problem, because the same rules are applicable. So what I thought was, I will introduce this new concept as well, so that when we think about the vertical load transfer, we can have many systems. So generally in a building, where the vertical load transfer is by the columns. But in this new technology, we are planning to make use of walls as well. So what I thought was, before we go deep into the design of columns, bases, foundations, I thought of introducing this new technology that we developed as a result of about 40 to 50 years of research at University of Moratuwa. The main feature of this particular technology is it can give rise to about 50% cost saving in a building. And the good news is from 22nd, 23rd, 24th, that is Thursday, Friday, Saturday, we are going to have Architect 2024 exhibition. And we are actually having a 30 feet by 30 feet space called Affordable Luxury, where we are going to showcase many new technologies. So if you are keen, please visit the exhibition and experience get a first-hand experience of these new technologies. So if I repeat, it is on 22nd, 23rd, 24th, Architect 2024 exhibition. We are going to have a special construction cluster called Affordable Luxury. So the idea is, you can have luxury, but at a fairly low cost. So you can learn firsthand about more details about this particular technology. So now if you look at the way that the construction industry in Sri Lanka has evolved, first we look at what happened in 2018 and what was the situation that remained in 2020. So we just do a small comparison so that we can get some deep idea about what actually happened. So 2018, what is the price of this? What is the US dollar? Used to be something like 165, 60 to 170 rupees. We just lose a range. Now we'll take 23, 24 values. US dollar has now come down to 310 to 320. But still you can see it's nearly double in rupee terms. Then we can also look at price of diesel. And so used to be around 120, 130 rupees per liter. Now it is 300 to 350 rupees per liter. It varies all the time. And then let's look at electricity. We used to have a unit maybe about 10 to 15 rupees. Today is about 50 to 90 rupees per unit. So you can see very significant variations in costs. And with that, what could happen? Let's see what could happen. So if you look at the basic ingredients that we use cement, sand, aggregates, concrete, and many other materials, and steel. Cement used to be around 800 rupees. Now today it's around 2,200. Now if you look at sand, good quality river sand today costs per cube about 22,000 rupees. Manufactured sand can be slightly lower. It used to be around 14,000. Aggregate cost would have been about 8,000. Today it goes around 12,000. 1 meter cube of concrete. Today, with placing, labor, everything can cost between 40,000 to 50,000. And used to be in the range of 22 to 25 to 30,000. Now let's look at steel. Per ton price used to be about 120,000. Today it has gone up to, I'm talking with the VAT, with VAT prices, something close to 350,000. But that is what we buy. But if you consider with the fixing charges, this used to be around 200,000. So today it is close to 450,000, 500,000 after allowing for wastage. Now, if you look at all these figures, if you look at steel, we can see clearly about 250% increase. And cement, these prices would have been 150% increase. So you can clearly see where our future should be. Our future should be structures that need less steel. So now we have to see whether Eurocode allows, on what basis that we go for this particular concepts. So for that, what I thought was, let's look at a past event where the whole world had similar problems, and that is 1945, end of Second World War. Russia was devastated. Germany almost completely destroyed. Europe needed a lot of renovations and rehabilitations. And England needed a lot of new buildings. But huge amount of resources have been used for the Second World War. So there were shortages. Steel, cement, and many other ingredients. Bandhuga, can you hear me?
Yes, sir, we can clearly hear you.
Yeah, okay, right. So we had a lot of shortages. And so, for example, we all know one very well-known engineer, Dr. A.C. Vishalingam. In 1950s, he went to Tokyo University. Tokyo University is the biggest in Japan as an undergraduate with a scholarship. And recently he published a book recalling his memories. And in that one he has mentioned, all Tokyo University had one car. All university had only one car. We know Japan is a country full of cars, but those days they had only one. Similarly, many other countries faced severe steel shortage. And those days, labor was material very expensive. Labor very cheap. People are looking for jobs and they were willing to work for low wages and have simple lives. So those days, if you look at CP 110, then BS 8110, both codes support something called rib slabs. Something like that. So the idea is we cast a slab to a thickness of 75 millimeters, and these can be about 2 meters, 2.5 meters. And the whole idea is this rib will be strong enough to span one way and ensure the deflection delta is pretty low. That's the idea. Now, if you look at this idea, how does it come? It comes from the behavior of a slab. Let's take an example. Because we know steel has ferrous, around it will be a ferrous oxide layer, and there can be various forms, Fe2O3. There are so many different varieties, but so let's just say it's an oxide layer, and cement has tricalcium silicate plus water, calcium silicate gel plus calcium hydroxide. This creates a lot of calcium hydroxide here. So if you look at concrete, its pH value is around 12 to 13. And this ferrous oxide layer is very stable when pH is high. So we have a stable environment, and provided that we introduce a cover of 25 millimeters or more, then we can have a structure that is going to definitely last 50 to 100 years, provided that we have cured concrete at least 1 week. Because curing of concrete will continue this reaction, and continued reaction means a lot of calcium hydroxide in concrete, and pH will be high, dense concrete. So curing is very important. So if we cure concrete, then the whole purpose of this crack control, cracked concrete, is to protect steel, And this, when we say cracked, we are talking about a surface crack width of 0.3 millimeters. But it rapidly diminishes in width, and by the time it reaches the reinforcement, it's negligible. So that's the kind of crack that is allowed. And so generally, we can't see any of these cracks because they are so fine, we can't see them. So now, then people thought, why are we having all this concrete? Cannot we remove all this concrete? But they found deflection is a big problem. Deflection is high when the thickness is low. So they could not do it. Then they thought, can't we have ribs, beams, and make the slabs as thin as possible? And when you make the slabs as thin as possible, span in this way, short distance, and having ribs around 2-meter intervals, what would happen? We can minimize the amount of concrete, steel, at the expense of more shuttering. False work may not vary because false work is something that we need less because our weight is less, but we definitely need more shuttering, more labor for shuttering. So after Second World War, material short supply, labor cheap. So this idea of minimizing worked well because materials are expensive and short supply. More shuttering was not a big problem because the saving from material would be much more than the extra work needed for shuttering. Then what happened? So this was after Second World War. It needed 2-3 years to recover, and the recovery came in early 1950s. And in early 1950s, there was another special incident that is relevant to today. And China was declared as a republic 1949, and then Americans got involved in a war with China through Korea. And it was a very damaging war until 1953. 350,000 Chinese died, 400,000 Americans and Koreans died, and finally the war ended having a ceasefire. They did not have an agreement, what they had was just a ceasefire. They said, okay, no more fighting. But during this time, China did not have much industry, but this war helped China to emerge, to improve their steel production. War helped China to improve their steel production. And they also wanted a lot of rubber. So, and they were producing a lot of, they had a lot of farmers, so they were producing a lot of rice as well. So they wanted rubber, they had a lot of rice, so Sri Lanka started supplying rubber to China. China supplied rice to Sri Lanka. So that is what we celebrated as 70 years of rubber rice agreement last year. So with all these developments, by 1960s, Japan was doing reasonably well, and they were also having a big middle class, and gradually middle class means wages rise and more production means material reduces. So gradually material prices started to reduce, wages started to rise. Then people thought, why we need ribs. Let's reduce labor because each rib is expensive. So get rid of ribs, go for solid slabs. They went for solid slabs. And rib slabs lost popularity. Rib slabs lost popularity. So then came 1970s and 80s. 1970s saw big trouble in 1973 October when OPEC countries, oil and petroleum exporting countries, decided no oil to USA, no oil to UK, and a lot of restrictions on other countries. And the oil prices increased rapidly. And this led to huge exploration on oil. And what happened? The economies developed a lot because restrictions forced other countries to explore oil. So one of the significant findings was North Sea oil. So with that, UK and Norway benefited a lot. These two countries, because the oil prices were high. And in UK, most of this wealth was used for economic reforms in the economy. In Norway, they invested this money. Today, Norway is one of the richest. And what they did was they gave 5-year visa to the people to work in the North Sea. And after that, and within 5 years, they mastered all these technology of oil exploration. And today, Norwegians are managing their oil resources. So a lot of people from UK went to work in Norway, but they could work only 5 years because within 5 years, Norwegians ensured that they are masters of the game. So then what happened was, so a lot of reforms, wages continued to rise, materials reduce. Then people thought, why we want beams? Let's have columns and slabs. So then flat slabs. And flat slabs, what is the problem? Flat slabs need a lot of steel. Lot of steel. So this was in 1980s, 2000. Then they thought, why reinforced concrete? Why not pre-stressed concrete? Which will allow us to minimize the amount of reinforcement. So tendons like this. So this pre-stressed. Now this was a world trend. So world trend in 1960s, 1980s, 2000 onwards. These are all different trends. Starting from ribbed slab to solid to thicker flat slabs. So that's the evolution that took place in the world. Now let's see how Sri Lanka responded. In Sri Lanka, our main exports were tea, rubber, coconuts. In 1960s, 1970s. So 1960s onwards, we did not have enough dollars. We don't have enough dollars. So we had to think of using less tea. That led to pre-stress concrete. Concrete being actively promoted by Dr. A.N.S. Colosimo. So we got PT bridges, bridge beams, and precast technology. So many things happened. So 1960s, we were well ahead of the rest of the world in technology. However, 1970 onwards, the closed economy. Many things were produced in Sri Lanka, but not enough. Not in sufficient quantities. So our construction lagged a lot. And Dr. Gulasinga served Malaysia because he found it difficult to work in Sri Lanka. So then came 1977 onwards, open economy. By 1990s, we started getting big companies like ICC, Maga. They were small companies those days. Sunken. And our engineers also got more experience. And we also followed the world trends. So what we did was, we also thought flat slabs versus solid slabs, solid beam slabs, beam slab systems. We also thought this may be better than this, because that is the world trend. But not only this, we even went to PT slabs. However, by 2010 onwards, we started hearing construction cost in Sri Lanka is high. And it is much higher than Malaysia. But we continued because we had a lot of money coming as foreign remittance, and so sometimes the money came through diaspora, so many different ways. So what we did was we kept on going, and until April 2019, where the blast rocked the economy. And then came COVID. Then came the devaluation of rupee. And as a result, we had a construction industry down to a very low level. And we had few problems. What are the problems? Too high cost per square meter. And construction is prohibitively expensive. So if construction is not possible, do not buy lands. Why? Because if you can't construct a building, why you want to buy lands? So this has a rippling effect on all. So that was the time we thought, now we cannot go on like this. Now we have to make a change. Because we had a lot of research and we had a lot of alternative materials. But no takers. Nobody is interested in all these new materials that came out as research. Once in a while, we get a client who is keen, and then we might use it, but it was never the mainstream. Right? So, if I give some examples of materials, we had Dura, there is straw panels, very good construction material, but only about 15 to 20% production capacity was used of the installed factory. Then we had cement stabilized earth used as blocks, rammed earth. Many people tried to make the blocks popular, but most of them failed. Only few are now remaining. Then lightweight panels. So there are so many options, but very few were interested. So that's the time we thought, what is the way out? What is the way out? And the way out is, let's see the fundamentals. So if you have a problem, first we have to understand the problem. So we try to look at the fundamentals. The reality of Sri Lanka is still, if you spend 100,000 rupees on materials, we need only 35,000 to 40,000 rupees convert it to a building. And if you compare this with Australia and Sri Lanka, Australia, one day labor 4,500 to 5,000 rupees. I'm talking about skilled labor. In Australia, the minimum payment for skilled labor is 50 Aus dollars per hour. So the cost can be 500 to 400 to 500 dollars because you have to pay for insurance. So many other charges are there. Social security, insurance, there are so many charges. So it can be 400 to 500 dollars. So rupees 100,000. But if you look at the cost of material, because we are using natural resources, there cannot be huge difference in the cost of materials. Because we also importing steel. So they also import. So the cost of materials cannot be very different. So what happened? So these people like flat minimum labor. And what should be our strategy? Minimum material. Like after the Second World War. So we thought, okay, let's see how this can be realized by making use of the modern research we have already undertaken. We have completed. The data is available. The technology is available. So let's adopt the technology and see how we can have minimum material and how it can give rise to cost-effective construction. And then you'll ask, why cost-effective? Because if we are to bring the people back to the construction industry, we need to be cost-effective. So we have to see how we achieve it. So that's what I'm going to explain in the next few slides. Bandhuka, is that clear?
Yes, sir. Very clear and very interesting, yes, sir.
Yeah, okay, fine, thank you. So now we have to think not inside the box. So we need outside the box. We cannot be thinking inward, we should be thinking outward. So that's what we need. So let's see what is the concept behind this minimizing the material. Now let's take sand. I will take sand from Manampitia. As an example, may be applicable for manufactured sand as well. So this is Sri Lanka. It has to come all the way from there to here. Maybe 250 kilometers. So diesel at 350. Loaded lorry might do only about 3 kilometers per liter. Maximum is 4. Because these are carrying huge loads, so maximum is maybe 3. So that means 200 rupees minimum per kilometer. So 50,000 rupees to bring only for the lorry charges, around 50,000 to bring a lorry from here. But you have to think about the lorry going back as well. So what they do is, now they have closed lorries, 10-wheelers. They bring material. So it comes as sand in the closed lorry. And it goes back with a load of fertilizer. So to Colombo from Manampitia is a load of sand. From Colombo to Manampitia, Colombo, it's load of sand. And when it's going back from Colombo to Manampitia, it is carrying all the goods that are needed for farming. So because of that reason, still we can buy 1 cube of sand for about rupees 22,000. Now let's see what is the meaning of this. And the bulk density is 1,500 kilograms per meter cube. And 1 cube is 2.8 meter cubes. So the weight of 1 cube is 2.8 into 1,500. Bandhu, can you find the value? This is the bulk density.
4,200.
4,200 kilograms. So then what is the cost per one kilogram? This 22,000 divided by 4,200. What is the value, Bandhuka? Comes close to 5 rupees.
Yes, 5.23.
Yeah, so rupees, let's say 5 rupees, right? Let's assume that it's around 5 rupees. Can be slightly more, right? Now, let's look at the cost of cement. Cost of cement. Cement is rupees 2,200 per bag, 50 kilos. 2,200 divided by 50. Bandhuka, what's the price?
44.
Yeah, so let's say rupees 45. Right. Because there can be some transport charges as well. So let's say 1 kilogram is 45 rupees. Okay. Then let's take concrete. 1 meter cube of concrete. We have cement around 300 kilograms. We have sand around 750 kilograms. We have water around 200 kilograms. Sorry, kilograms. These kilograms. So 500, 1,250. So this should be 1,250 aggregates. Now, aggregate also cost will be 12,000 rupees divided by 4,000. It also can be about 4,500 because the bulk density is slightly higher, about 1,600. So what is the price? 12,000 divided by 4,500. So earlier we got 4,200 as the weight of 1 cube. So we say 4,500 kilograms.
2.67.
2
2.67.
Yeah. Say, shall we say 250?
Yeah. Okay.
Shall we say 250? Because sometimes you can get aggregates at a slightly lower price. So let's say it's around 250. Now we can work out the cost of concrete, sand, aggregate, water. I have done this calculation earlier, but I never showed how I got these numbers. 5 rupees for sand and all that. Can you remember, Dubey?
Yes, yes, sir.
We calculated, but I never told you that how I got all these numbers. Now today, we multiply this by 45, multiply this by 5, multiply this by 250. And what are the values, Bandhuka?
13,500 for cement.
500, yeah.
3,750 for sand. 3,125 for aggregates.
Shall I say 3,200?
Okay.
Then what is the addition? I'll make this 3,800, right? Okay. So 13,500 plus 3,800 plus 3,200.
20,500.
Rupees 20,500.
Right.
That is the cost of materials for 1 meter cube of concrete. Without labor, no labor. And then if you are making it a ready mix plant, then that involves transport, which can be about 1,000 to 2,000 rupees depending on the distance per meter cube. Right. So this is how we say 1 meter cube of concrete can cost around 40,000 to 45,000. Sometimes it can be as high as 50,000 when we go for higher strengths. But generally we say it's around 40 to 45,000. So can you understand how these figures come, Bandhuka?
Yeah, it's clear.
Yeah. Now, so if that is the case, we are paying for material, we are paying for the volume. And when we say we pay for the volume, we are actually paying for the weight. So if you are paying for the weight, how to reduce the cost? Reduce the cost. How to reduce the cost? Reduce the weight. Now how to reduce the weight? Optimize. Now how to optimize? Now we have to think about what the people did after the Second World War. When material was expensive, labor was cheap. So this is what they did. Ribbed construction with 75 millimeters of slab and something like 200 millimeters of rib. They went for something like this. And then this is a small span, so you need a minimum amount of steel. And it can come even as a 8 millimeter bar. And you might need little bit of steel here just to make sure the continuity. And that also can come with 8 millimeter. Why? Because these are thin concretes. So whatever we do, we can have a greater control because we are dealing with smaller quantities. So when we looked at this possibility, we thought in Sri Lanka, we must go one step further. Why? So what is the advantage of solid versus ribbed? Solid may be 125 to 150, can go up to 170. Ribbed 75 to 90, and overall thickness is 100 millimeters. When you allow for rib thickness and everything, might not be even 100, but let's say 100. Then we are saving, let's say we save 50 millimeters each floor. 50 multiplied by 25 kilonewtons per meter cubed. How much we save? 0.05. How much we save? What is the weight, Bandukha? 0.05 multiplied by 25.
1.25.
So each floor we save 1.25 kilonewtons per meter square from a conventional solution. And let's say we have a 40-story building. 40 multiplied by 1.25 is saved. How much we are saving?
50.
50
Yes.
kilonewtons per meter square. Now can you see that lightweight could have many advantages even in a multi-story construction? A slab, minimum slab thickness can be extremely useful in multi-story construction. But this may have a time factor because we see a lot of rainfall, lot of work for formwork. So that's where we looked at again some of the research completed very successfully, leading to PhD at Marathon University, and that is the lightweight slab systems. And this is how the lightweight slab system comes. We have a precast beam, 175 millimeters thick, 200 millimeters deep, for up to 4.5 meters spans. Then we place these beams at 2-meter intervals. So these are variation from the original designs where they use 1.5 meter original research. Then what we did was we looked at it, how we can improve it according to Eurocodes. So this can be 45 to 55 millimeters. And we are having these slabs. Then we wanted continuity. So let's see. Okay, let's have a rib like this. Have the reinforcement here. And then place a screen. Then you might say, oh, this can be dismantled. How to prevent it dismantling? We run a reinforcement here, and and a locking reinforcement here. We lock each slab by using a 8mm cut piece, small piece of steel. And we like continuity. So what we do is we provide some top reinforcement here, some top reinforcement here. Then what do you have? Now we have a precast system with a precast slab with in-situ topping. And what is the beauty of the system? Because we have ribs, what is the deflection? Is almost equal to 0. Because during the construction we can have props for this, and a prop for this. So once you place a prop in the middle, then we complete the slab. And then we remove the props after concrete has hardened. So these days, you know, the strength development curves are very rapid. So if we keep this moist and cured with ponding for 1 week, concrete will gain a huge strength. So after 1 week, we can remove. And we can precast all these members. Precast. We don't have to worry why the columns and all the other things are cast, foundations are done at a casting yard created on the side of the same site if the space allowed. Then we can start casting this. And this is the main innovation that we did. So now I'm going to draw an exaggerated, a bigger enlarged view. So this slab. So this. We have this. And because we are placing only 35 to 45 millimeters, only a small quantity of concrete, we can use admixtures, improve the workability, because 1 liter of admixture can cost about 600 rupees, 400 to 600 rupees per liter. So by using admixtures, we can reduce the water content and we can get high quality concrete like 30 to 40 megapascal concrete for the screed. And even these can be about 30 to 40 megapascal concrete. Because higher the strength, lesser the cover required. Because we are going for thin construction. So if you are going for thin construction, we know in concrete, cement is the friend, what is the enemy? So reduce the enemy by using admixtures. So that with the same amount of cement, you can get high strengths, like 30 to 40 megapascal. And once you go for something like 40 megapascal concrete or 45 megapascal concrete, the ingredients are the same, but the durability is very high. We can reduce the cover requirements. Anyway, these slabs are cast like this with a lock. And you need cover blocks, reinforcement. Try the other reinforcement. These are all 8mm bars. Y8, we get 420 bars or 420 into 6, about 2,500 meters of steel reinforcement when we buy 8 millimeter. So you can see per ton we get a length of about 2,500, so we can minimize the steel. And these 8 millimeter bars at 150, 75 here, 75 here will be adequate. On the other hand, we can cast it to 450 millimeter thickness if a tower crane is available for lifting. So if the tower crane is available for lifting, we can cast it for 450 with 150 with the reinforcement at 150 centimeters. Then you need 3 bars like this. So these 150, 75, 75. So altogether 450. So there are two widths that you can cast. But if you are not having a tower crane, the weight of a panel should be less than 100 kilograms. Then 2 people can handle it. Otherwise, we need 4 people to handle it. So those are the issues that the construction manager should resolve depending on the type of equipment available at the site. So we complete this for 90 millimeter, 90 to 100 millimeter. We try our best to reach 90. Then what we can do is we can get marbles, chips, can be terrazzo chips or 4 to 6 millimeter chips. What we do is these all, lot of grout will be here. We embed these materials and let it harden. And by using a float, you can make all these materials firmly embedded. And then we can, once hardened, we can cut and polish with a terrazzo machine. And you can get whatever the finish you like. And another technique is get broken windscreens. And what do? You lay broken windscreens, you crush it and embed broken windscreens also, pieces also in between. And so you can get extremely nicely finished terrazzo finish without spending money on floor finishes. That's one alternative. What is the other alternative? Other alternative is we have the same thing. Now I'm not going to draw all the layers. Let's assume that it is all completed. And we have completed this perfectly level. These 90 millimeters, these 2 meters. Then what we do is we mix 1 tile grout with 1 fine sand. Now generally the tile grout is laid for about 8 to 10 millimeter thickness. Here we lay this mix for a 15 millimeter thickness and lay the tile directly on it. Lay the tile directly on it, giving a total thickness of around 125 millimeters. Now let's compare this with what we generally do. 150 slab, because we are concerned about the sound insulation. Then we have around 40 millimeter tile bed. Then we'll use around at least 5 millimeter grout and tiles. So what is the overall thickness? Maybe about 200, 150, 200, around 200, about 200 to 210. And we save 75 millimeters. And we can use an average density of 25. So that is 0.075 into 20. How much is that, Bhanuka? Madhuka?
It's 1.25.
1.25 kilonewtons per meter squared is saved per square meter. Got it?
Yes, sir. Yeah.
Right. So what you do is, now we have lightweight. So because this is lightweight, so let's take a house, possibility for a house, just to give you an indication how this can be used in apartment buildings having 7-8 stories. So just look at a house having a garage like this, and the entrance here, a bedroom here, a washroom here, and these are all the living area, and the staircase here, and so these the, so here you can get door, and this may be the entrance. So this is the bedroom, and so this may be about 6 meters. This may be another 6 meters. It's a large house. So what can we do? Now some maybe there may be walls. This may be a wall. So this is a lightweight system. And let's say this is 8 meters. So every 2 meters we have a beam. Then we'll place the slabs. So what happens? This is lightweight. So part of the load is transferred there, part of the load is transferred here. And loads are transferred at intervals. And now you can see if we use a strong masonry can carry a part of the load. Concrete frame will carry the rest. So that means, because this system is made by us with precast elements, we can, for example, for this bedroom, we can decide we are going to have the beam this way because this is a wall. This is a wall. The windows are here. We might say, okay, so I'm going to have the slabs this way. So this wall will carry the weight of the beam because part of this slab will go into this wall and part of this slab will go into this wall. So what you see is very good two-way distribution of loads. If that is the case, you can decide. We run the main frame elements only in one direction. And we carry all the other elements this way. We are going to have the slabs this way. And we are not going to run a frame this way. Because these walls can be load-bearing walls. This can be load-bearing walls. So the moment you start thinking like this, you'll find we have a very good load distribution. So it's lightweight and it's hybrid. Why hybrid? Because loads are going all over the directions and we are carrying part of the loads using masonry. And it can be used for multi-story. And apartment buildings. And what is the beauty of this system? Because the deflections are strictly controlled. We reduce the number of operations. Like what? First thing, no tile bed. Use high quality bricks, high quality cement blocks. Although we call them cement blocks, they are concrete blocks. Why? Because the manufacturers, the reputed manufacturers use chips. Manufactured sand. They use chips, manufactured sand, and high quality cement. So it's a concrete block and very low water cement ratio. So they are concrete blocks that can easily reach 5 to 8 megapascal compressive strength. And the Euro code 6 tells us with M4 mortar of 4 megapascal. When you know the block strength, M4 mortar is 1:5 mortar. 5 to 8 megapascal compressive strength, what happens? We get 2.5 to 3.5 megapascal wall strength. Or you can even go for something like 4, depending on the strength of the blocks. And to minimize the weight of the blocks, we don't have to go for solid blocks, we can go for hollow blocks. We can make use of hollow blocks. So what is the concept? Concept is we have less weight in slabs, less weight in walls. Instead of 225 walls, we are using 150 walls. And these blocks are high quality. So if you construct the walls carefully with due attention, you can make a perfect wall that does not need plaster. And there's a product called Macao Super Plaster, which is a very water resistant product, polymer based. So you can have 3 millimeter, 2 millimeter. Thin plaster. And then the door and windows could be out of aluminium or timber. But how you fix it is all the aluminium work is fixed with anchor bolts. So even timber frames can be fitted with anchor bolts. Because earlier, early days we made the frames like this. So there was a portion here to fix but these days we don't use it. We make the timber frames also like aluminum frames, so that we can, by using anchor bolts, we can fix the system. All those things are available in Sri Lanka. So the whole idea is reduce materials, operations. In doing so, reduce cost. And you might ask, what is the cost? You can hit 2,500 rupees, 25,000 rupees per square meter for the structure, and you can complete a structure for 50,000 rupees per square meter. So, what do you think, Madhukar? The concept?
It's very interesting, sir, and I think we should take this to the construction industry.
Yes, because if we take this to the construction industry, there will be plenty of people who are willing to construct again. And the beauty of this system is this can be used in tall buildings, medium-rise buildings, houses, rooftops, you name it. So if you are doing a rooftop, why the rooftops leak? We do solid slabs, they sag. And then water stagnates. And with time, due to creep deformations, these sags, and we have problems. But here, we have a slab which does not deflect, lightweight, and very deep, So this can be altogether 300 millimeters deep. What you can do is you can lay the screed to a slope. Maybe the screed here may be 60. The screed here may be 40. So you lay it to a slope and you use all these marble type materials and make the top surface rough. The moment you do this, you will find waterproofing is not essential. It's not essential. So there are so many things you can do, because the whole idea of embedding chips here is, rather than having a concrete cement-based surface, what is exposed to the rain will be a chip-based surface. And we know chip-based surfaces are much harder and erosion resistant than concrete-based or cement-based surfaces. So the whole idea is we spread pre-prepared mix of pebbles, marble pieces, terrazzo chips, you name it. It can be glass chips, anything. That is hard materials. And then use a float and firmly embed those things into the concrete, fresh concrete. And why we can do all these things is we are not in a hurry, because we are dealing with small quantities of concrete. Whereas, you know, when you are doing a slab, it's a massive operation. Everybody is in a hurry. But here we are talking about small operations where nobody is in a hurry. So we have plenty of time. So this is some technology that I learned in 1985, 86, working with Toda Construction of Japan. Toda was a big company. They have operated a lot in Singapore, and they did Labuma Kaltua rehabilitation project. And they never had extra operations because Japanese labor was very expensive. Their method was lean construction. So it's lean construction. So the future is lean construction. And this has been completely developed at Morato University. So I developed it fully by using all the research. I use the research done by various other people, published work, and developed this method fully. So today, we have actual examples where these methods have been used for very cost-effective construction. And so we call it lightweight, hybrid, multi-story construction. And this can easily go up to 4-story houses, 8-story apartments, and with little improvement, my gut feeling is we can go up to 12 floors. So just imagine 12-floor apartment as much lighter than a conventional one, needing much less material, having hybrid load carrying systems with minimum plaster, and the floors as terrazzo floors or tiles on terrazzo type floors. You can achieve very significant cost savings. And this is our future. So
there's a question.
That's
there
what.
are,
Yeah.
There's a
What are the
question.
Yeah.
Is
Can
it
you read?
possible to provide provisions for services for electricity?
Yeah,
like
actually,
that?
there are two options. One is, because we are having screed, because we are having these panels like this. Two panels will be like this. So you can run the conduits here, right? Because the screed is going to come here. Got it, Bandhu?
Yes, got it.
But the other option is, because we are saving so much money. You can have, by embedding timber pieces here in the beams, or by keeping the conduits here, we can have a suspended ceiling from these beams easily using Eltero board. Eltero boards, these cement fiber boards that are manufactured in Sri Lanka. So we can easily create a ceiling underneath, and all the services can go in any direction, because we are saving so much money in the system. We can afford to have a ceiling, or otherwise we can easily provide services using conduits within the, because we can alter the arrangement. So one arrangement that was developed earlier was this. These slabs need not be unique. They can be any arrangement like this. So those days we used to run services here. Then we thought, okay, that's a little bit of extra work. So let's cast the panels like this. So we can provide the services here. Likewise, providing services is not a problem at all. So that's the first question.
Yes.
What is the second one?
So, what is the cover criteria when provided minimum thickness? Is it
Oh
possible
yes,
to apply for
cover goes with Europe.
adverse weather conditions like that?
No, cover, that's why I told you just one moment. I'll share the screen. Voice durability. See, this is the durability. And these are the exposure conditions. So we go for XC3. XC3. And here we have XC3. XC3, members with slab geometry, position of reinforcement not affected by construction process. It says reduce the class by 1. Reduce the class by 1. And then it says, if you are going for C3545 concrete, reduce the class by 1. So you can reduce the class by 2. So instead of S4, you can try S2. What is the core requirement? 15 minutes. Got it?
Yeah, got it.
So that's why we use admixtures and go for, because the main advantage is, because we are using very little concrete, we don't have to bring ready mix. We can use site mix, where we use the admixture, minimize the water content, use the vibrator, compact the concrete as much as possible, and minimize the water, because we don't want much workability, because we can use a vibrator and vibrate the concrete in the panel. So anything above 15 millimeters is accepted, because you don't need this delta. When you look at the cover, there's a delta factor, the 10 millimeter, because we are casting, we are not working on the reinforcement. We are casting on the ground. We are not working on the reinforcement. So this tolerance is not necessary. Tolerance is not necessary. So we need, what we need is 15 mm. See, what we need is 15 mm cover, because we are using very high strength concrete, where the cover to the reinforcement can be assured, because we are not working on it. We can buy cover blocks, because cover blocks are readily available in the market these days. So we can provide 15 mm, or if you want, you can go for 20 mm. Okay, Madhukar.
Okay, sir. And
So
how
we can
low?
design for Eurocode. We have designed it for Eurocode. So there's no problem of designing it for Eurocodes.
Okay, sir. Yes, sir.
What
And
else?
how low must the prop be provided until the concrete reaches its
Yeah.
strength?
So basically, I mean, these days we know when you go for high strength concrete, this high strength is we are going for high strength not for the flexural strength. We are going for high strength for durability. So if you are, even if you design this as a 25 megapascal cube strength, that is enough, because this slab is, we are not going to load the slab immediately after removing the props. You want few people walking and attending to the work, right? If you are, so as long as you are not going to store material on the slab, the moment the screed concrete cubes reach 25 megapascal, you can remove the props. But we are doing it in the range of 35-45 megapascal concrete, because we have minimized the water cement ratio. So what happens? We can easily remove the props after 1 week of ponding, 1 week of ponding. That is my personal experience. Okay. So basically now this is a departure from our general thinking. Okay, maximum we can do is 30 megapascal concrete. All that is gone. Now we are thinking about 45, 50 megapascal concrete with admixture even in small sites. Because spending little money for admixture, reducing the cover, going for a minimum thickness, they are all advantages. So our task is minimize the processes, minimize the materials. And if it means little extra labor, doesn't matter, because labor is very cheap. What we have to save is materials. Okay, well?
Okay, sir. And there's a question, I think we discussed this. Any provisions, considerations when it's directly exposed sun or thermal heat effects using
No,
as roof rope?
actually, this is what we do. This is a good question. It's a very good question. This is what we do. Now, in a normal slab, we have beam, and you might have a wall, all that. So what we do is, in this particular one, so we have this arrangement. But when you have a roof, what we do is, we make this beam little larger and place a bitumen sheet. You know, blackish color bitumen sheets that we use as a roofing material. And then we place the slabs on that. Then we place the concrete. Now, there's a positive connection between slabs and the beams. So the situation is like this. We have beams. There's a separation. And we have slabs made continuous with. So this can have expansion easily. and we can create a slope. So as long as there's a slope, we don't have to worry because water will go out. As long as we are removing the water, no problem. But the beauty of this system is deflection is zero. So there's no sagging in the slab. Because most of the time you will find due to creep, shrinkage, slabs sag. And this sag causes water to stagnate. And when the water stagnates, then all the problems will come and waterproofing problems will be there due to that reason. So what we can do is we can embed chips so that chips will not wear out, though the cement can be washed away, but not the chips. So we create chips here. And then use rooftop for planting fruits and vegetables. You keep pots like this, plant, and so there will be shade, right? So these can be specially made so they do not touch the slab. So what happens when you do all these things? Or you can put a polythene here, do something. What happens when you do all these things? The rooftop is readily used, and it will have, or you might have solar panels covering the rooftop. You will do something, and you might have an off-grid system, off-grid DC system, direct current system, because you don't have to convert it to AC, and use a small inverters, DC to AC inverter. Say you want to use an electric kettle, use a small DC to AC inverter and use the kettle. Because this is the decentralized system which is much cheaper than centralized solar systems off grid. So what you do is you will have two wirings in the house, one wiring for CEB, another wiring for this DC system. And you will have a separate bulb system for the DC system. So whenever you have a solar, you can have your own solar system. You don't have to be connected, you don't have to connect the solar system with the grid system. You can have two systems, and you can save a lot of money used for lighting, boiling water, and so on. And even if you have electric car, you can charge batteries. You can do all those things with DC. You don't have to go for AC, alternating current. So there are so many different options when you have a rooftop. And rooftops will be ideal because we can have many users with the rooftop. Okay, Madhuka.
Okay, so the last question.
What I say is we cannot be thinking inside the box anymore. We
Yes,
cannot be concerned about conventional. We must start thinking completely fresh, new. And that's why, we like all of you coming for this exhibition because many of these things will be showcased at the exhibition. So we like all of you coming, learning firsthand because it will not be just exhibits. We'll ask you to, tap a ramdal wall, or you might ask you to drive some stools and see how the Dura panels can be connected. So there will be many things, live exhibition. So if you have time, please come and learn firsthand. And it is, so we are spending over 1 million to make this happen. So we like all of you coming and, learning the state of the art in lightweight hybrid construction and so many new materials that are available for us to be very innovative and make our construction industry viable again. Okay, Bandhu?
Okay, sir. So the exhibition is on 22nd to 20.
22nd,
right?
23rd, 24th. I think it's Thursday, Wednesday, Thursday, Friday, Saturday.
Okay.
This month. Very close. I mean, not tomorrow. Not tomorrow. The following Thursday, we are having the exhibition.
Okay, sir. And
Right.
there are two more questions.
What is that?
Is there any effect of the cold joint between two stages of concrete and how to overcome it?
No. What we do is when you're casting, that's a good question. Excellent question. When you're casting the slabs, so we need to lift it. So what we do is when the slab is cast, it will have a hook like this for lifting. Okay. So so we run a reinforcement and lock this. So this is used for lifting. But after lifting, placing, we put a reinforcement through all these hooks and connect all the sets. Got it?
Yes, sir.
So we run around 400 millimeter, 500 millimeter centers. We run some for 8 millimeter bars in both directions and connect everything. So this slab is a mechanically locked slab. Although it's a precast, we are not relying on the bond. Bond will be there. We can generate the bond, but we are not relying on the bond. We are relying on all the mechanical connections. Got it?
Okay, sir. Got it. And the last question, could you describe further the explain precast slab plus screed method and monolithic construction requirements?
Oh no. Actually, this slab has been developed experimentally, and there has been cast, tested, and then designed. This can be designed as well because these are all mechanically connected. You when you are designing, this is how you do the design. Now let's say now we have the slab, the beam. Then we have the slab. So this bearing can be this 175. So we keep about 75 here. This 50 bearing. Bearing is 50. Then we have this next. Okay. So we consider all this as a flange beam. So what we design for Eurocode is a flange beam. What is the reason? The reason is we are having links like this, other reinforcement and locks. So this will be a composite action, not due to bond, but due to locking. Okay. So we designed this flange. For this beam, we designed this to carry the construction. Once you do that, you have hooks and all those connections and all that. So it is all one unit now. So what we do is we design a 90 millimeter slab to span 2 meters. According to Europe. That's all. And we make it continuous also. Now to make this load carrying capacity is more, we put some reinforcement here. 8 millimeter bars, very little reinforcement. And make it continuous. So these slabs are now going to behave like continuous slabs. This slab, 90 millimeters. Beam is going to behave as a flange. So This one system that can be designed for Europe. Have I answered the question adequately?
Yes, yes, correct,
Right?
sir. It is clear.
Yeah.
Okay, sir.
Okay.
Okay, sir.
Anything else?
I have 2 more questions. May I put them in the group, sir? Since
No,
we are
no, no.
running.
I mean, we are not. It's okay. You can ask.
Um, what about the vibrations due to less thickness?
Oh, no. The slabs over 90 millimeter slab over 2 meters is more than enough. And you know, slabs can vibrate, but beams will not vibrate. So this is a beam system. So I have used it over 6 meters. 6-meter beams, zero vibration, no vibration.
Okay.
Vibration can be suppressed. You can design for vibration when you are designing because vibration depends on the reflection. There are research papers. You can download these research papers by CESC. On ISL, you can readily download. CESC alternative slab systems will allow you to download it. ISL papers. There the vibration is handled. So you can just see. Vibration is based on deflection. If the deflection is zero, vibration is zero. Okay?
Okay. Okay, sir. And so, is there any significant cost saving compared to rebars and the normal beams? There's one question like that.
Yes. Actually, you can do this, complete this slab for about 800 rupees per, 8,000 rupees per square meter, whereas the conventional can go up to 1,400, 500, because you know, this is very cheap when the spans are large. And anyway, this is a very cost effective system because you don't have to spend for shuttering. The reinforcement is less because you know reinforcement is very expensive. So whatever reinforcement you save is a huge save. So that's why I said, you know, if you use this method, you can complete the structure for 2,500 rupees per square, 25,000 rupees per square meter, or 2,500 rupees per square foot. If you ask anybody, everybody will say, oh, sir, to complete the structure, the minimum is 8,000 rupees these days. This is a huge saving. Every corner we are saving, and the unbelievable saving. Okay, Bandhu?
Okay, sir. And I think chairman said in the sectional committee, Engineer Mangasila was there, but things are disconnected for some reason.
Right.
Thank you very much, sir. Today's lecture was very interesting, and there are many positive feedbacks in the chat box as well about this method. And so hopefully we will be able to take this to construction industry in future.
Yeah, so it's up to the engineers to take it. So that's why we are using all these exhibitions. We are doing everything possible to make the professionals understand that conventional systems, we have not taken it properly because we have copied too much. And in copying, we have adopted inappropriate systems that are good for countries with high labor costs.
Yes.
Because in our system, the material cost must be is very high. So what you have to save is material, not the labor. So by going for more materials, less labor, we have made our construction industry extremely expensive. So we have to go back. And I can give you one example. In 2015, I had to give 50,000 square feet in 2 months for a hospital project. And I designed a building with concrete floors, but these concrete floors are on steel beams, composite systems. And these beams, these slabs, so I use precast slabs, pre-stressed concrete. Do you know what is the thickness of the slab for 6 meter span? 90 millimeter. And Even today, you can go there, no vibrations, absolute no vibrations in the structure systems. And so they are using it as the hospital. Absolutely no problem in the system. And cost-wise, those days, 2015, the cost per square foot was 7,000 rupees, and I completed it for 3,500 rupees. So my systems always, my target is minimum 50% cost saving from the conventional systems. So the system that I presented the systems, or if you put everything together as a lightweight hybrid multi-story construction, the construction saving can be anything between 50 to 60%. Okay, Bandhavan?
Okay, sir. Thank you very much, sir. It was really interesting today. And how about our next session? It will be on the continuation of this. So,
Okay, next session. I think now we have got this in.
Yeah.
We can go back to columns, foundations,
okay, sir.
masonry design. So this will need masonry design also. Again, no. So first we'll complete what we started before we go
Okay,
to
sir.
more masonry design. So we'll discuss columns, foundations, cellular rough foundations. So there are so many things we can talk. Again,
Okay, sir.
associated with this lightweight hybrid construction.
Okay, sir. Okay, sir. Thank you very much for this,
Okay,
sir.
right, thank you.
And
Thank you,
we
Vandana.
will share that exhibition file also if available in the group.
It's a architect 2024
Okay,
file.
sir. Okay, sir.
So if you ask, if you just go into Facebook or Institute of
We will find it.
Architecture, you can
Okay,
find it. Yeah.
Okay, sir.
Okay.
Okay,
Okay.
thank you very much,
So
sir.
our one is only 30 by 30 feet by 35 feet area, full of things that you never expected, full of
Oh.
surprises,
Okay,
right?
sir. Okay, sir.
And new technology, new methods, a lot of live exhibition, not like a dead exhibition where you see something has already been made for you. It's not like that. You will come and do things there.
Okay, sir. Okay, thank you very much, sir.
Right.
And also, I would like to thank the chairman, Civil Engineer Section Committee. He was there until the end, and now he left for some reason. And I'd like to thank Mangala Silva, the chairman, Civil Engineer Section Committee, for continuing this lecture series, and also the ISL Secretariat, Publicity Department, and the IT team for these hosting arrangements. And also, I'd like to really appreciate the participants who asking questions and for their enthusiasm and interest in the subject. It is really valuable for this lecture series, and we hope you will join our future sessions as well. Thank you very much, and good night, everyone. Thank you, sir.
Okay, thank you very much.
Okay, sir.